For the next example, I was going to do number 27, but I realized that I've already done it, and the video has already been made available to you. I just didn't call it number 27 to show you what I mean. If you go into Canvas, go into announcements where I posted the announcement about what you should do before Monday. And in the series of videos that cover integration by partial fractions, the very last one says examples of three-term quadratic factors, or case 4, three-term quadratic factors. And the last one, an example of three-term quadratic factors. I'm not going to play this video for you, but just show you what I mean. It's a one where the denominator is quadratic but can't be factored, so you're stuck with it. It involves completing the square, and I invite you to watch the video. But I was about to do it here and realize that I've already done it before. So I would go look at that last video in the announcement that says what you should do before Monday to see an example of that one, because number 28 is going to be in your homework, which is like it. I do want to take a look at number 35, though, which is not like one I did a video on previously, but I want to demonstrate one where we combine techniques. Square root of x over x minus 4, and this one's actually a definite integral. That's just going to change how it ends from 9 to 16. And this doesn't look like a partial fraction decomposition, but when you're doing a substitution, usually you do it to try to fix things or make things better. It's recommended in the textbook what you should let u equal. But if we were doing a substitution on this to begin with, I would probably focus on the square root, because the square root is what's mucking things up here. Now, I guess we could say let u equal x minus 4 and make the denominator a single variable, which might be beneficial, but would it be? In fact, let's just chase that rabbit for a second. If we said let u equal x minus 4, then we would have du is equal to dx, so that's good. But we would also have x equals u plus 4. And upon making the substitutions, well, let's not worry about the limits of integration yet. The denominator becomes u, the numerator becomes the square root of u plus 4, and we have du. And I'm not sure if that makes things any better, because now we just move the binomial from a denominator to inside a square root, which doesn't make it any better. So that substitution really doesn't get the job done. But sometimes a substitution will not finish the problem, but make it look better. For example, if we said let u equal the square root of x, and in the book it actually says use the substitution first, then what does that give us? Well, if we were to solve for u before we took the solve for x before we took the derivative, then u squared would be equal to x, and 2u du would equal dx. Let's go ahead and change the limits of integration while we're at it. X equals 16 implies u is the square root of 16, which is 4, of course. And x equals 9 implies u is equal to the square root of 9, which is 3, of course. So we can completely transform this to an integral in terms of u. Instead of from 9 to 16, it would be from 3 to 4. The denominator changed the x to u squared, so we get u squared minus 4. Now it's looking like partial fractions. The numerator just becomes u, but the dx becomes 2u du. If we pull the 2 out in front, I don't know if we need it or not, but we'll pull it out in front, and then multiply these two u's together on top, we get u squared over u squared minus 4 du. Okay, well, now it's partial fractions issue, except the denominator's degree is not larger than the numerator's degree. So we're going to have to do some division. And because the denominator is not just a linear divisor, it's u squared minus 4, synthetic division would not get the job done. We would have to use long division, knowing full and good and well that there is a way to trick out synthetic division, but let's not go there. U squared plus 0, u plus 0 is the numerator. U squared minus 4 is the denominator. I guess if you wanted to, you could put u squared plus 0u minus 4 to represent the missing u term. It's not going to be critical in this problem, though. How many times is u squared going to u squared? Well, once. And then 1 times the divisor is going to give us u squared plus 0u minus 4. Subtract. U squareds cancel. OU's don't matter. OU's, 0 U's don't matter. And then 0 minus -4 is 4. So we end up getting a remainder of 4, which is going to go over our divisor, u squared minus 4. So that was a little messy, but it is what it is. All right, so 1 plus 4 over u squared minus 4. Before I write it down, I want to show you a little bit sleazier way to get there. This is not traditional, but it sure is convenient. There's the integrand. Wouldn't it be nice if there were -4 up there? Because that would equal 1. I can throw a -4 up there if I balance it with a +4. And then I split it into 2 fractions. This fraction ends up equaling 1. The other fraction is 4 over that, which is exactly what we got with the long division. It's a delicate game to play, balancing out the numerator so that you can find the denominator in the numerator and then split and then cancel some stuff. Or you could just do the long division. 1 plus 4 over u squared minus 4 du. Let's go ahead and split this. The first integral becomes 2 times the integral from 3 to 4 of 1 du. Shoot, that's going to be easy. Plus 2 times the integral from 3 to 4, don't forget the 2 distributes, of 4 over u squared minus 4 du. Well, that's going to end up equaling 2. I shouldn't have to explain why. The antiderivative of 1 is u. But the other one is going to be a partial fraction decomposition. So I am going to leave this here and go to the next page, since my online office hours are almost over. 2 integral 3 to 4 of 4 over u squared minus 4. Let's just go ahead and set up the partial fraction decomposition. U squared minus 4 factors into u minus 2, u plus 2. And let's do the partial fraction decomposition down here. 4 over u squared minus 4 is equal to a over u minus 2 plus b, that's got to be better, plus b over u plus 2. This one shouldn't take too long. If we clear out the fractions, we'll get a 4 on the left. We get a times u plus 2 plus b times u minus 2. Notice I didn't actually write the fractions and talk about what's going to cancel. I just know it's going to. If we let u equal 2, we're going to get 4 equals 4a, because this guy cancels. This implies a is equal to, it's a horrible looking arrow. This implies that a is equal to 1. And if we let u equal -2, we get 4 equals -4b, which implies that b is equal to -1. Okay, so 1 in the first fraction, -1 in the second. It's going to be pretty easy now. Both of these are natural logs. Don't forget the 2 in front. 2 natural log absolute value of u minus 2 plus a -1 makes it a minus natural log absolute value of u plus 2. And this is all going from 3 to 4. We put in 4, we get natural log of the absolute value of 2. 4 minus 2 is 2. Don't really need the absolute value anymore. Minus 4 natural log absolute value of 6. And then minus 2 natural log absolute value. When we put 3 in here, we get 3 minus 2 is 1. Well, that's going to be 0. Natural log of 1 is 0. Minus the natural log of the absolute value of 3 plus 2 is 5. So let's see. We get 2 natural log absolute. We don't need the absolute value. It's already positive. Minus 2 natural log of 6. And then plus 2 natural log of 5. But be careful, that's not the answer to our final question, because we also had this integral here. Let's go ahead and work it on a separate page. I'll just highlight those separately. I mean, it's an integral that you should be able to do without much to do, if you will. Integral from 3 to 4 of 1 du. Well, 2 times that integral. The integral of 1 is u, going from 3 to 4. 2 times 4 is 8. 2 times 3 is 6. 8 minus 6 is 2. Therefore, 3-dot triangle. The original integral, which is from 9 to 16 of the square root of x over x minus 4 dx, is equal to the first integral's answer plus the second integral's answer, 2 ln 2 minus 2 ln 6 plus 2 ln 5, 2 ln 2 minus 2 ln 6 plus 2 ln 5. I really want to condense the last 3. Set up 1 log, it's going to be a fraction. The positive logs numerators, the positive logs arguments go in the numerator, so 2 times 5. The negative logs argument goes in the denominator, so 6. The 2 is in front because I factored a 2 out of all these before I condensed them. If we're going to factor, might as well factor out a 2 again, plus times 1 plus natural log. In that fraction, we can reduce the 2 and the 6, and that leaves us 5/3. I'm kind of curious what the answer in the back of the book is, because this is number 35 from section 6.3. So we're going to take a look real quick, just because I'm curious. 6.3, 6.3, number 35. They have 2 plus a natural log of 25/9. Oh, they distribute the 2. And then they put the 2 on the power of the 5/3. 5 squared is 25. 3 squared is 9. You see, the problems like this is like, where do you want to stop? Well, I want you to demonstrate that you know how to do the problem. If you had gotten here and stopped, I'd be like, great, that's awesome. The rest of it is just showing off.